Okay, so how many remember substitution rule from calculus 2? You certainly have used it, right? But uh, substitution. Okay, Jamal remembers substitution. We all love substitution. And the thing is, substitution, you can think of it like, so like for here, you're making an integral of x. You're making a change of variable in a substitution. Now in the box there with a 1 by it, okay, you're making a substitution. Okay, you let u equal function of x, but in turn x is a function of u. And if you were to write this integral of f of x dx, if you were to write it in terms of the new variable u, the integral would have changed limits c and d, where you have a function of g of u, and dx becomes g prime of u du. Okay, that now you don't really, when you do the substitution, you actually go through the steps and work it out concretely. But in fact, symbolically, this is what you're doing. This is what you're doing. Let me just see here. One moment. Hold on, class. Yeah, that's symbolically what you're doing. And so you can think of this, since x equals g of u, okay, g prime of u could be thought of as dx du. Okay, and so what happens is you get this dx du in, when you make the change of variable, you get a term there, dx du. So this is the formula, the formula for a substitution of one variable. Okay, a formula for a substitution of one variable. But sometimes, like in multivariable calculus, when we have a function of 2 or 3 variables, we would maybe want to make a substitute. We would want to make a substitution for the 2 or 3 variables. Okay, we would want to make a substitution. So analogous to this result here in calculus 1, we have a result in multivariable calculus that says the following. Let me find it here. So, for instance, you could let x equal a function of u and v in a double integral, and y could be another function of u and v. That would be your substitution. And if you do that, okay, let me just go right here. Change of variables in double integral, okay, would be you're going from you have a double integral where you're integrating over a region R in the xy plane, and the region R through the change of variables in x and y, the region R gets transformed into this region S that lives in the UV plane. So region R is in the XY plane, region S is in the UV plane. And you have this factor in there, okay, this factor, this with these absolute value signs on it, but the absolute value, so it's the absolute value of what's called a Jacobian. A Jacobian. So what is a Jacobian? This partial of xy over partial of uv. Well, Jacobian is defined, okay, as the determinant whose a 2 by 2 determinant with partial derivatives The first row is the partial derivative of x with respect to u and v, and the second row is the partial derivative of y with respect to u and v. Okay, that's called a Jacobian. And they prove this absolutely amazing result in section 12.9. But I think I'd like to just sort of help you feel comfortable with some examples, and I'll let you look at the proof on your own. But it involves what it involves. Maybe I can just sort of quickly go through the idea. So, you know, the idea here in figure 3 is you're taking a region R, and through a substitution, you're transforming the region R into a region S. So the region R is in the XY plane, and the region S is in the UV plane. Okay, and you can think about a parameter, a vector R, that's a function of u and v, and through that they formulate how they go through a proof where they actually arrive at the result I just showed you, and it involves finding the areas of parallelograms that approximate, well, I want to say this the right way. It involves finding areas of parallelograms. So the proof is actually, it would take probably about half an hour to go through the proof. Please feel free to do that on your own. I want to try to get to some examples, and I think the examples will help you, help give you an intuitive feel for what we're doing here. This is just, section 12.9 is an extension of the substitution method that you learned in Calculus 1. Only you're substituting for multiple variables. So I think what I'd like to do here is just go right to a few nice examples. Okay, let me make this visible to you. So in this example, well, let me let you copy this example down, and then we'll talk about the solution. Okay, so let me give you a moment to do that. Okay, so section 12.9, change of variables and multiple integrals. So as you know, we're focused now on double integrals, okay? As you know, the region D is essential to know what region you're integrating over for a double integral. For a triple integral, it would be a solid. But for a double integral, it's a region. And in this problem, what we want to do is we have a substitution where we're going to let u equal x plus y and v equals x minus y. Now, yeah, okay, that we're just going to do that. And what we want to do is we want to find the image of a trapezoidal region with these vertices. We want to find the image of the trapezoidal region R with these vertices. And the image is called the image S, by the way. The image S. So what we do is we draw the trapezoidal region as you see here. Trapezoidal region, I have the vertices 1, 0, 2, 0, 0, negative 2, and 0, negative 1. Okay, there's the trapezoidal region R in the XY plane. Okay, and I've also labeled 4 sides of the trapezoidal region. Side 1, 2, 3, and 4. Okay. All right. So and remember that u is going to equal x plus y, and v is going to equal x minus y. Okay, so let's focus here on the first side here, side 1. Okay, side 1. Okay, that's this line segment. Now, how do we describe the line segment? Oh, all right. The line segment is y equals 0, where x goes from 1 to 2. So how would that line segment be transformed under this transformation? Well, u equals x plus y, okay. Y equals 0, so u would equal x plus 0, and that's just x. And v would equal x minus 0, and that's just x. So that means that since u equals x and v equals x, v would equal u. See, I need to get an equation in terms of u and v, because my region S here, the horizontal axis is the u axis, and the vertical axis is this v axis, the v axis. So I have a u and a v axis. Now u goes from 1 to 2. I don't want to say this here. Maybe you can ignore limits. You can't ignore the limits. Those are important. I don't know why I wrote that. I guess it was because I thought maybe it complicated things. But no, we really do need it. Because, look, v equals u, but what are the limits on u? Well, u equals x, and x goes from 1 to 2. So that means u should go from 1 to 2. So if I want to graph v equals u, where u goes from 1 to 2, well, that's going to be right here. That's 1 prime. Now that prime doesn't mean derivative. It just means side 1 got transformed into this side here that I've highlighted. Are there any questions on that? Okay, well, let's look at the next. Let's look at side 2 here. Side 2 here. There's side 2. Okay, that has the equation y equals x minus 2. Y equals x minus 2. Hold on, and I want to just have that. Yeah, y equals x minus 2. And x goes from, hold on, class. X goes from 0 to 2. Okay, well, what would that line segment be under the transformation? All right, well, again, u equals x plus y. So I want to say this the right way. Hold on now. Yeah, y equals x, y minus x equals negative 2, and x minus y equals positive 2. But let me just, one moment here, class, one moment. One moment, class. Okay, so u equals x plus y. So that means u would equal x plus x minus 2, because y is x minus 2. So u equals 2x minus 2. Okay, the fact that x is between 0 and 2, if u equals 2x minus 2, that means then what would the range be on u? Well, u would have to be between negative 2 and 2, because when x equals 0, u would equal negative 2, and when x equals 2, u would equal positive 2. And then any x values between 0 and 2, u would take on values between negative 2 and 2. Okay, but now let's focus on this. V equals x minus y. So if y minus x equals negative 2, by virtue of the fact that y equals x minus 2, y minus x equals negative 2, that means then that x minus y equals positive 2, and hence v must equal 2. And this is therefore v equals 2, and the limits on u are u goes between 2 and negative 2. Hence, the second side, that line segment, the second line segment would get transformed into this line segment. Are there any questions on that? Are there any questions so far? Please stop me if you're uncomfortable. Okay, well, let's continue on here. Maybe I'll go green here now. Third line segment. Oh, okay, Robin, the domain of u. So for this the transformation of that line segment. So I mean, v equals 2, definitely v equals 2. That's a constant. So in the UV plane, that's a constant horizontal function. Okay, but what is I need to know for what values of u v equals 2 is active. Okay, well, there's a little bit. Let me just kind of. So V equals 2. Okay. But U, remember, U equals x plus y. U is equal to x plus y. If I can draw the line V equals 2, right? That's a horizontal line in the UV plane, but I need to know what the limits are on U. The horizontal line doesn't go on forever, right? So for what's the domain? So U equals 2x minus 2. Well, if x is between 0 and 2, and U equals 2x minus 2, then U, the limits on U would be between -2 and 2. Because if U equals 2x minus 2, what's the smallest value of x? X equals 0. Well, that will go with U equals -2. What's the largest value of x? X equals 2, right? Right, that's the largest value of x. So then for that, then U would equal 2 times 2 minus 2. That means U equals 2. So then the U would be between -2 and 2. And that's how we got this. All right, very good, Robin, very good. So then here is my second transform line segment. Let's go to the third line segment in this region R, this boundary. That is given by the equation x equals 0, and y goes from -2 to -1. Okay, and remember, U equals x plus y, and V equals x minus y. Okay, so let's see here now. All right, so I gotta relate the x equals 0 to the U and the V. Well, I know that if I were to add these two equations here, I would get U plus V equals 2x. But x equals 0, so that means U plus V equals, U plus V would equal 2 times 0. Hence, U plus V equals 0, or V equals -U. So V equals -U would be the line, the transform line. Now, what are the limits? What are the limits? Well, again, x equals 0. U is going to equal 0 plus y then, so U equals y. Well, y is between -2 and 1, so that means that U is between -2 and 1. And so if we graph the line V equals -U, which for U between -2 and -1 here, well, V equals -U would be, this is 0 right here, right? That's 0. This is 1, 2, -1, -2, right? So V equals -U looks like this. And it ends at U equals -1, and it begins at U equals -2. A little bigger there. That's side 3 transformed. Are there any questions so far? We've now got the region R is closed, so the region S in the UV plane is also closed. So naturally, the final boundary is going to be this. This is going to be the transformation of side 4. Well, now side 4 is going to be equal to the line y equals x minus 1, where x is between 0 and 1. So y minus x equals negative 1. That means x minus y, this is really implies, right? That means x minus y equals positive 1, so v equals 1. And the fact that u equals x plus y means that u equals x plus x minus 1, u equals 2x minus 1. And so the fact that x is between 0 and 1 means that u is between negative 1 and 1. And that's going to get you that final side. And this is how you transform a region R into a region R in the xy plane into a region S, right? A region S in the UV plane. So when you transform the integral, you're going to have new limits, right? Your old limits are with respect to x and y. The new limits are with respect to u and v. Okay, based on the formula 9. Let me see. Let me bring it up real quick here. Hold on. One moment, class. I'll bring that back, but one moment. See? There's the formula. And you see that you're transforming your integral over region R to a new integral over region, you're transforming your double integral over region R, where region R is in the xy plane, into a new double integral over region S, and region S is in the UV plane. So that's how we get the result that we got. Are there any questions on this? All right, so we're going to do an example now. We're going to do an example where we're actually going to need to do a change of variable in a double integral in order to compute the integral. Let me stop the recording on this. But the region that we're going to have, well, I'll tell you what, I'll keep it all together since this next example is related. It's related to this quite nicely. So let me go ahead and, are there any questions? Okay, let me bring over the next example then. Okay, let me give you a moment to copy this example down. Okay. Okay, so in this problem, we want to find the volume of solid that lies under this surface. Okay, this surface here. Okay, and maybe I'll just write the surface equation down here of that function. I don't know why that does that. Sometimes that does that. I don't know why. Let me do it again. Hold on. Let me use my stylus. Okay. Okay, who wants to integrate this function? Who would want to? I'll tell you what. Hold on. I got it. I got a better idea. Hold on. Come on. This is the problem. I knew it would kind of. I have seen this, incidentally, this section 12.9 kind of problem in my own classes in graduate school. Okay. Who wants to integrate? Who wants to integrate that? Double integral. So this is the volume, right? The volume for we have a surface. We have a solid that's bounded above by this surface, this function, and below by the xy plane over a certain region R. So for a double integral, this is how we would find the volume. So what do you think? Do you want to try to integrate that? I mean, dA, in this case, dA, of course, we have to figure out what the limits are. But dA is going to be, let's say, dy dx. Okay. Do you want to try integrating? Let me just hold on. So the inner integral, and I was pleased on the exam, people were using their numeration, like, their little symbols here, the parentheses and so forth. Can we integrate this function with respect to y? Can we do that? Is there an antiderivative of that function with respect to y? Ryan says no. I mean, who would like to do that? Who would like to try integrating that function with respect to y? Is there anybody here? Or who would definitely not want to integrate that function with respect to with respect to y and x. I guess I'll ask it this way. Shall we try to integrate this function with respect to the variables y or x? Chat out a thumbs up or a thumbs down. Okay. Eric says no. Who says thumbs down? Who says thumbs up? Maybe chat it out here in the okay, Jamal's thumbs down, Robin's thumbs down. Okay. Eric's thumbs down, both Eric's are thumbs down, Ryan's thumbs down, and you're right. You cannot integrate that function with respect to the variables x or y. Oh, so gee, that just like in calculus, when it's difficult to find an antiderivative, we initially try substitution. All right. So, all right. I'm going to let u equal something and v equals something. What do you want to let u equal? What would be a natural choice for u? And a natural choice for v? U equals something. Okay, Robin's suggesting let u equal x plus y. Okay, and Christopher's saying let v equals x minus y. That's right. That's right. And u equals x plus y. So these are the same transformations. That's the transformation that we did in the first example we looked at. And by the way, the region in the xy plane with these vertices here is the same trapezoidal region that we looked at in the first example. So I'm going to show you a page quickly, but in the solution, but you've seen it already. So first thing we have to do is we have to transform the region R in the xy plane into a new region S in the UV plane. And we've done that. We did that. So we don't need to worry about doing that again. We don't need to worry about doing that again. The next step is to find the Jacobian. The next step is to find the Jacobian. And that's what we do here on the next page. So we know what region S looks like. And we know u equals x plus y and v equals x minus y. Well, that means then that u would equal, see, we have to figure out what x is in terms of u and v, and under this transformation t. We have to figure out what x is in terms of u and v, and we have to figure out what function y is in terms of u and v. So I say to myself, okay, well, u plus v equals 2x, and u minus v equals 2y, so therefore x equals u plus v over 2, and y equals u minus v over 2. And based on that, we can compute what's called the Jacobian. This is called a Jacobian. How many maybe have seen a Jacobian in another class? Not too many of you, maybe. Okay, Ryan's seen it in differential equations. Yes, absolutely. Absolutely. Okay. Very good. Very good. So what we're doing is we have the determinant of a 2x2 matrix whose elements consist of the partial derivatives of x with respect to u and v on the first row, and the partial derivatives of y with respect to u and v on the second row. And the book proves why that has to be that way. Well, the partial derivative of x with respect to u is going to be a half, and the partial derivative of x with respect to v is going to be a half. Similarly, the partial derivative of y with respect to u is a half, and the partial derivative of y with respect to v is negative a half. That's a negative a half. Okay, and so, hold on here. Absolutely fascinating, really. But I'm trying to make this just look a little bit nicer here. This is a negative a half. Okay, so we get then that the determinant, or the Jacobian, I should say, equals negative 1/2. The Jacobian equals negative 1/2. And then what we have to do is take the absolute value of the Jacobian to get a positive half. Please let me know if you have any questions. All right. Are we ready to move to the next page? Let me know when you're ready. Robin's good, okay. And John's good, wonderful. Okay. Okay, well now, let me just go back to the book here for a moment. Okay, let me go back to the book. Again, this is our change of variables formula for a double integral. All right, just so now I'm going to show you the next page in the solution, and you'll see it corresponds exactly to what you see here. All right, so let me go back into so we're right here. We found the absolute value of our Jacobian. And so our volume, okay, that's our volume, right? Our volume can be re-expressed as this double integral with respect to s. There's e to the u over v power. The 1/2 is the Jacobian. And we're integrating with respect to, we have it down as du dv. Now we could have had dv du, by the way. I could have had dv du. But for some reason, I want to integrate with respect to u first, as opposed to v. I want to integrate with respect to u first. Now, why is that? Well, we'll come back to this page. So if we go here to the figure S, okay, which you've drawn. This is the figure here, right? Figure S. Well, all right. So if I were to do dv first, okay, if I were to do dv first, this would be treating region S as a type 1 region. Right? How many double integrals would be needed to evaluate the volume if we treated region S as a type 1 region, as you see here with these blue vertical arrows? How many double integrals would be needed to compute the volume? Hold that thought. I'm giving you a hint with the coloring I'm doing. How many times? So the top function here stays the same, always, the top function. But the bottom functions, how many times does the bottom function change across the region? How many times? 3. That's right, Robin. So if you were to do dv du, if you were to treat this region S as a type 1 region, you would need to compute 3 double integrals and add them. I don't think any of us want to do that. So let's try treating region S as a instead of a type 1 region, let's treat it like a type 2 region. Type 2 region, okay. Type 2 region would be where I have horizontal lines. And I'm bounded by a function on the left and a function on the right. The function on the left and the function on the right stay consistent throughout the entire region S. So we would only need one double integral. Now let's see here. What are my boundary functions here? What are my boundary functions? Well, on the left here, let's do the right. Remember, this is the, hold on here. This is the, 0 there. So on the right, I have the function v equals u. We learned that. But of course, I would write it as u equals v. And on the left, over here, I have the function v equals negative u. Right, that's his function here. V equals negative u. But of course, I would write that as u equals negative v. So this is my function on the left, and this is my function on the right. And that's going to provide the limits. That's going to provide the left and right boundary functions for this transformed double integral. The v limits are going to go from 1 to 2. From 1 to 2. Are there any questions on that? It's all on the recording as well, but let me know if you have any questions. We'll get back to the example then. I mean, back to the, we'll finish up the example. All right. Well, then, so my volume becomes then this double integral. And would you not agree this is a much easier integral to work with? With the V is volume, right? Isn't this a much easier integral here to work with than the other integral? The other double integral? Yeah, it absolutely is. It absolutely is. John agrees. Thank you, John. So that being said now, if I iterate my integral, and I was pleased on the exam, people had done this. Like Nema, I saw you do that on your exam. Use the parentheses and the iterating on your double integrals, so that was good, and other people too, but I just mentioned Nema's name, very good, and I hope you don't mind that. All right, the antiderivative of e to the u over v with respect to u, we hold the v constant. This is the antiderivative. If you differentiate v times e to the u over v power with respect to u, you will get your original function back. We substitute in v, and negative v for u. V over v is equal to 1, right? The 1 comes from v divided by v. And the negative 1, that comes from negative v divided by v. And then we'll put in the 1 and the 2. The antiderivatives of v times e and v times e to the negative first are respectively given here. We'll put in the 2 and 1. And in the end, your answer is going to equal 3/4 times the quantity e minus e to the negative first power. And that is an exact answer. An exact answer. A computer's not going to give you that answer. Right? It'll give you a very, very good approximation, but you know what I'm trying to say. If you were to do section 12.1 where you inscribe bricks underneath the surface and then make the bricks smaller and smaller and maybe use the midpoints to decide the bricks, what the bricks are, and add up all the little volumes of the bricks, you're not going to get an exact answer as good as that. How many think this is absolutely amazing, this concept, this idea? Okay, John likes it. Good, good. And you notice it's quite a bit more work, right? Regular substitution isn't a whole lot of work when you just transform one variable. But when you transform two variables, it creates more work. Are there any questions? I want to show you one more thing here. Okay, everybody's good. All right, everybody has this copied okay? This corresponded, by the way, to example 3 in your textbook. Example 3. The key really is picking the right transformations on your variables. That determines what your region S is going to look like. And usually in these problems, it's kind of obvious what the transformation should be. Okay, what the transformation should be. So, okay, let me bring up then the book here. Okay, so I want to just show you. Okay, so you can also work with three transformations. What I mean is you can transform X, Y, and Z. X, Y, and Z. And they do that. They have that here. And the Jacobian is as you see there. As you see. And then there is the formula for a triple integral where you transform all three variables. And what they do actually here, it's pretty cool. Pretty cool. In example 4, they use that formula to derive a formula for triple integration in spherical coordinates. Okay, they do that, and you can look at the example, but they make this like, you know, going from x, y, z to in spherical coordinates, going from integrating with respect to rectangular coordinates to spherical coordinates. Here are the natural substitutions that you learned from spherical coordinates. They compute the Jacobian and they work it out, and you actually get the formula. One moment. Just please ignore that. That's usual telemarketer, right? How many get a telemarketer call every day? How many of you get that? I don't know. Do you all? Okay, Robin does. Eric, okay. John 5 times a day. Well, you see, it used to be, class. Well, let me just comment. So remember how with triple integrals with respect to spherical coordinates, the dv, which is rho squared sine phi d rho d theta d phi, that geometrically they supported that back in section, well, in 12.8, but now you have another way to confirm that that's the right what's the word I'm looking for? The right volume unit. Okay, and they show it here in example 4. So it's pretty cool. It's pretty cool how they go through that and show and work that out. They work that out using the formula above. So hold on here. Let me get this. Are there any questions? Any questions on this at all? Okay, let me stop the recording.